derivative with hydration of any of them should produce the acid. Alright. And once we are done with the basic identity of acid and its derivatives, and again we had a basic idea about the commonly used reagents to convert an acid to the derivative. We'll want to learn the process, the mechanism a little more closely, where if you look properly, this part of the molecule R C double bond O is certainly retained. So this is retained, OH minus is lost at the expense of Cl minus, RCOO minus, R prime O minus, NH2 minus or R NH minus coming in. Yes or no? Yes or no? So it could be looked upon a nucleophilic substitution, because you will find a nucleophile going out, Cl minus nucleophile going out and accommodating another nucleophile. So converting an acid to its derivative or hydration of a derivative to an acid would be another kind of nucleophilic substitution, And in course of discussing the mechanism and how it is different from the nucleophilic substitution we have learned before, we are also likely to arrive at some results, some order, which are directly indirectly asked in different exams. So I want all of you to be very attentive, and in the process we will be using some basic theories of and basic ideas of general organic chemistry. Well, and then it could be between the derivatives, you might want to convert an anhydride to an amide, a halide to an amide, and any of these reactions I would be trying to convert an RCOX to an RCOY, where X and Y will be variable for an acid or its derivative to get converted into each other. Yes or no? All of it would be carried out at this carbon atom, and maybe this to that would require a nucleophile Y minus, a nucleophile coming in, another nucleophile going out. That's how my first impression of the process was nucleophilic substitution, and the only way or the very way it will differ from SN1, SN2 which we saw for the alkyl counterparts, alkyl halides, would be the fact that I'm carrying out this nucleophilic substitution on a carbon atom which is not called alkyl but acyl. It's an acyl carbon. So right away it's different from SN1, SN2 or nucleophilic substitutions which we have seen before. We've seen aliphatic nucleophilic substitution, SN1, SN2, maybe a few cases of SNI which I did for you, and then aromatic nucleophilic substitution where we're into figuring out the structure of Meisenheimer complex. Yes or no? Chlorobenzene to phenol, aniline. Somewhere we learned a benzyne mechanism for aromatic nucleophilic substitution, but here it's a different story altogether, because we're trying to carry out a nucleophilic substitution over a acyl carbon. Now because it's about one nucleophile coming in, another nucleophile going out, all these reactions would fall under a common name. They'll be called trans-acyl reaction or trans-acylation. The process will be called trans-acylation. Acid to acid halide, acid to ester, ester to acid. Yes or no? We'll call them trans-acyl reactions or trans-acylation because one nucleophile comes in, another goes out at this acyl carbon atom. Fine. And in general, before I go into the mechanism of trans-acylation, if this is what I was doing in the alkyl counterparts, and I was trying to convert alkyl halide to another halide or alcohol, or vice versa, it could be by SN1 or SN2, the aliphatic reactions. Now, as I've already told you, while comparing it with the aliphatic counterparts, certainly we know about the mechanism of SN1 and SN2, and the very way this is going to differ from those reactions would be the fact that it's occurring at acyl carbon atom. All these reactions I told you will be clubbed together as transacyl reactions. Now tell me, in general, although again it will be subject to so many factors regarding the nature of the reagent and the attacking nucleophile and solvent and other factors, in general, what do you think? Between transacylation, which is acyl nucleophilic substitution, and alkyl nucleophilic substitution, which should be more feasible? Which should be more feasible? Think over it and excuse me for a minute. Alright, maybe the same nucleophile coming in, the same nucleophile going out, one occurring over acyl carbon, another over alkyl carbon, which should be more feasible. Maybe, the C double bond O, you realize is going to be polarized towards oxygen, O minus C plus, and at most, due to electronegativity of X, this carbon can have some positive charge. But I repeat, at most, that positive charge will be partial charge by inductive effect. So some positive charge over this carbon atom would be by inductive effect only, whereas this will be a more defined positive charge, resonance, mesomeric effect, and it's going to be more inviting for a nucleophile. It's going to be more inviting for a nucleophile. Yes or no? So henceforth, in general, if you have a situation of this kind, RC double bond O and RC double bond OCl, and you have a nucleophile to attack this compound between CCl and COCl, and if you have a nucleophile to attack this particular molecule, this could attack this carbon as well as this carbon, but certainly attacking here is more likely because this is having a more defined positive charge. So between acyl and alkyl carbon, a nucleophilic attack over acyl carbon is preferred. Alright. So transacylation is going to look like more feasible than the corresponding alkyl nucleophilic substitutions, and then not only electronically, even sterically, a thought could be this carbon is sp3 and this carbon is sp2. Now in sp2 the bond angles are larger, with the arms more widely spaced. Well, even sterically, because this carbon has 4 arms around it and this carbon has 3 arms around it, the bond angle in sp2 and sp3, both electronically and sterically, where because of sp2 the bond angle is more, the arms are more widely spread, sterically also, and certainly we've seen electronically, attack over an acyl carbon is going to be easier than over an alkyl carbon. Now if we are happy with the fact that transacylation is going to be easier than, or is going to be more feasible than the corresponding SN1 SN2 kind of mechanism, still we'll want to explore the mechanism of transacylation, where yet again, while doing it in alkyl halides and while learning the possible mechanisms which we later on termed SN1 SN2, here also the initial thought could be, it could be one step or 2 step. A 1 step process would mean this coming in, and right away in the same step this coming down and x minus going out, and it could be represented in one step only. And I can also think of a two-step process where this y minus going in is going to give you, well, a tetrahedral intermediate. This carbon becomes tetrahedral, this carbon becomes tetrahedral. A tetrahedral intermediate in suppose the first or the slow step of the process. Yes or no? And this in the fast step could get converted to the final product, and we can also think of a two-step process. I hope again I am very clear on this part. The mechanism could be a one-step process where a y minus is directly substituting x minus, or it could be a two-step process where the slow step is about y minus attacking the nucleophile attacking, forming a tetrahedral intermediate, the way we had for carbonyls, and this in the fast step losing x minus, producing the final product. We'll see that this is going to be the actual method. This is going to be the actual method, which is a two-step process through a tetrahedral intermediate. This is going to be the real mechanism. It's going to be a two-step process. Transacylation will be a two-step process involving a tetrahedral intermediate. And although the intermediate could not be isolated, and the intermediate is generally not isolated, because it's an ion, which we know is stabilized by minus I effect, a strong minus I effect instead of R. Suppose if I have a strong minus I effect, CF3, C fluorine atoms, and the compound CF3 C double bond O, OC2H5 sits a particular ester of trifluoroacetic acid. Take it as a kind of story associated with this process, that a strong minus I group like CF3, and then if the nucleophile in the slow step is going to look like CF3 CO minus OC2H5 and the nucleophile here, we've been able to isolate this intermediate. This intermediate could be isolated because of strong minus I effect and the negative being stabilized. This kind of intermediate could be isolated. This intermediate has been isolated, but other than that, it's difficult to isolate and then concretely justify this mechanism. Indirectly, we can prove it though. One such attempt was taking a strong minus I group CF3, and we are able to isolate the corresponding intermediate and prove that this is the mechanism. Another method could be by studying the corresponding energy profile. We have seen energy profile of different reactions. A one-step process and the energy profile will have just one peak. A two-step process of this kind, and if this is the true mechanism, energy profile of this kind is expected. Yes or no? The first with a higher peak, the second with a lower peak. Again suggesting it's a two-step process, where the first step is the slow step and the second step is the fast step. So I could plot the energy profile and confirm it's a two-step process. Also, it could be proved by the study of the corresponding, both these steps. You could study the corresponding Gibbs free energy change and the entropy changes. And suppose we go into the study of the entropy changes in both these steps, it found that in the slow step, the first step, you see this peak is higher, suggesting the activation energy is more. And in this two-step process, the first step is slow and the second process is fast. You all relate to it? You all could relate to it? Again, authenticating a two-step process And when the corresponding del S entropy change was seen, it was found that del S of the process is negative. Yes, I've told you before in different topics that an increase in entropy would mean more number of particles, and decrease in entropy will mean lesser number of particles. So decrease in entropy will always suggest addition, condensation kind of processes. So because the del S is found to be negative, this mechanism is further authenticated that certainly two particles are becoming one particle, and a slow step formation of tetrahedral intermediate is maturing to the final product. Yes or no? And if we are done with the basic understanding of the mechanism proposed, we might want to go into the individual acid derivatives and see, depending upon the nature of X or Y, how easy or difficult it's going to be carrying out the different transacyl reactions. I hope you all have copied it. As I told you, we'll want to again keep it simple, derive some facts, orders from the first principles of organic chemistry, and say if these are the derivatives known to us could be same or different, R and R prime could be same or different. We'll see that the reactivity of acid and its derivatives in transacyl reactions will certainly depend upon the group which is attached to it. And then because we have to relate the order of reactivity of these compounds depending upon the difference in the nature of this group only, we'll want to focus on these groups only, and some point of time where this is going above and this going out, it's going to involve the leaving tendency of the group. We'll see that the order of reactivity will involve the leaving tendency of the group. Yes or no? And leaving tendency being antagonistic to basic behavior, things which I have told you before, basic property is or basic nature is to donate a pair of electrons, leaving tendency is to come out with a pair of electrons, and because you know that leaving nature or leaving tendency is kind of inversely related to basicity. To find the order of leaving tendencies, maybe I have to fall upon the order of basicity, and again to find the order of basicity, maybe I'll have to fall upon the acidity of the corresponding acids. So we'll want to do it that way only. Suppose if the corresponding acid is HCl, the corresponding acid is RCOOH. There, if it's water, alcohol R prime OH, ammonia, and an amine, don't you think this is the order of acidity? This is the order of acidity. Yes or no? Yes or no? And if this is the order of acidity, I guess I don't need to explain this because you've been doing it over a period of time. Strong acid and organic acid, water, aliphatic alcohols are less acidic because of a plus I effect. Ammonia is a base, and with more plus I effect, a 1 degree amine is going to be more basic. So this has to be the order of acidity of these particular compounds, and thus this would be the order of basicity of the corresponding bases. This would be the order of basicity. This would be the order of basicity, and as we understand that, more basicity will mean poor leaving tendency. If this is the order of basicity derived from the order of the corresponding conjugate acids, the reverse has to be the order of leaving tendency. The reverse has to be the order of leaving tendency. So Cl minus being the weakest base is supposed to be the best leaving group. Cl minus, out here the weakest base is supposed to be the best leaving group, and NH2 minus or amide anion would be like poor leaving groups. And while converting these compounds to another derivative or an acid, will need to involve transacyl reaction where this group has to go out, and if the order of reactivity has to come out of the order of leaving tendency, which we have been able to establish this way, again from the very first principles, if Cl minus is the weakest base and the best leaving group, don't you think this would be most energetic, most reactive, and amides or N-alkyl amides should be least reactive? So when it comes to the order of reactivity, this has to be the order of reactivity towards transacyl reactions. This has to be the order of reactivity towards transacyl reaction, because if it has to depend upon the leaving tendency of the groups, X minus has to go out to accommodate Y minus in any of the transacyl conversions. We'll want to again obtain it from the very first principles. We'll understand acid halides will be the most reactive and amides or its derivatives will be the least reactive. Halides will be most reactive because Cl minus or X minus is going to be the best leaving group. Yes or no? Yes or no? And this is where, although I gave you basic understanding of how we are looking to prepare derivatives from the acid, practically, because you realize it would be the easiest and most feasible to carry out a transacylation on acid halide, we'll see that practically to convert an acid to an anhydride or to an acid to an amide, acid to an ester, practically we'll want to convert the acid to the halide and then we'll want to carry out the transacylation reaction. What I mean is, because we understand that halides are going to be the most reactive of the group, practically while trying to convert an acid to an amide, this is what is done. Instead of directly reacting upon the acid, you might want to convert the acid to a halide and this to an amide, or once you have converted it to a halide, it's going to be easier maybe obtaining the other derivatives. It's going to be easier certainly obtaining a mixed anhydride, allowing two acids to interact with each other. You'll get a mixture of three anhydrides. Yes or no? So the best way to get mixed anhydride would also mean converting it to a halide and then maybe treating it with R prime COO minus. Out here you'll need an R prime OH, and here you might need NH2 minus or ammonia. Yes or no? And practically we'll want to convert an acid to the halide and then carry out the transacyl reaction, because you understand this is the most reactive halide or this is the most reactive acid derivative. Again, one thought could be, if Cl minus is easy to replace and is the best substrate to carry out transacylation, how is this so feasible? How Cl minus could displace OH minus? Although it will also depend upon the number of particles, the concentration of different species. It's not like if I give you an order of the kind which I gave you before, you can't have an amide converted to an acid. It's not like OH minus cannot replace NH2 minus at all. Certainly we know OH minus is a better leaving group, NH2 minus is a better base, but it's not like you can't convert an amide to an alcohol, because the mechanism will actually reveal different leaving groups, sometimes very different from what we are expecting. And certainly while converting an acid to a halide, it's not like directly replacing OH minus with Cl minus. The most popular reagents, SOCl2, PCl5, PCl3, we'll see the mechanism will be different, where RCOOH plus SOCl2 giving you RCOCl plus SO2 plus HCl will be the most popular method again. SOCl2, PCl5, PCl3, we'll see that all the three could convert acid to halide. All the three are the very popular reagents converting COOH to COCl. COCl2 will be the best of the following. Who will tell me why? Because the byproducts are gaseous too. Sulfur dioxide and HCl will go out. I don't know if it's a common school question also, because in different batches, I've found people always answering it. SOCl2 is a good reagent out of the three, because the byproducts are gaseous. With PCl5 along with RCOCl, what is the principal byproduct? POCl3 with PCl3. What is the, which is S3PO3? Here you get S3PO3, and with PCl3 you get POCl3 and water. So this again looks like something which is, asked in school exams, or you'll want to keep a note of it. This is the most popular reagent because the products are byproducts are gaseous. With PCl5 you get S3PO3, and with PCl3 you get POCl3 as the principal byproduct. But nevertheless, I am able to convert RCOOH to RCOCl using any of the reagents. Alright. And on any kind of acid, on any type of acid, aliphatic, aromatic. Very quickly, say the mechanism. I'll give you one mechanism only. Questions from the mechanism of these reactions are very unlikely. SOCl2, suppose gonna look like this, and if this lone pair attacks this sulfur, this is how the first compound will look like. RCOOH, S double bond OCl, this oxygen might be positive. Fine. It's called protonated alkyl chlorosulfite. Again, it's not necessary, you'll want to know this name like anything. Protonated alkyl chlorosulfite plus Cl minus plus Cl minus plus Cl minus. Okay. And now this Cl minus will replace a group which is not OH minus. So as I told you, it's not like we'll directly want to substitute OH minus and bring in Cl minus, because that will look less feasible. Yes or no? Because you'll feel Cl minus is a good leaving group. But indirectly, using a reagent of this kind, I'm able to do that, because you find that Cl minus is not going to speak to RCOH directly. After this process, this step, Cl minus will attack here, and this is going to be a good leaving group for reasons like this oxygen is positive. So there is a strong tendency, to get this pair of electron. This positive oxygen will make it a good leaving group. And in the process, if you get RCOCl and